Okay. And in this room it's probably better to use this in order not to be out of voice in a couple of hours. Okay. Not really. Hello, hello. Probably the rack is off, but I can manage without them. I have no idea how to turn that on. And you can hear me fine. It's just my problem keeping the volume low. So let's go back where we left. You can see the screen, everything is in good order. I have my files under desktop, and then our folder, and then practical activity on flow duration curve. Are you following me? Everything is fine? Good. This time, instead of opening RStudio, selecting the folder, I will simply double click on the script. So the script is this one. I will double click on it. This will open an instance of RStudio. But please do check this. The working directory should be already the right one. In fact, if I open the tab Files, I see the content of the directory I want to work in. And if I go down here in the console, can you see, or this is in the way? You can see the last line? Okay. If I want to check, if you remember, dir, like directory, open and close brackets. If I see exactly the same list of files here, I'm good to go. Okay? If you don't see the same list, you do like last time. You navigate towards the folder and then using the gear set as working directory. But if you see the file list, we're good to go. Last time we stopped at line 73 and this program remembers it. So if I click on the script now, I have my cursor here blinking. In order to find ourselves exactly at the same point where we left, I simply have to select all the lines from 73 up. I select them all. Okay? So I'm pressing and holding down Shift and select all the lines, then Control or Command, depending on your system, and Enter. This will run all the commands. If you see some red instances, please check them. If they say error, it's a big deal. It means there's something very wrong going on. If it's a warning, or can be okay. You remember this warning message? It's because I asked the program to plot some zeros on a log scale. So 0 goes to minus infinite, and it's a problem. It's signaling that there's a warning, but it's not a big deal. I have this diagram, and the first figure we generated was the period of record flow duration curve. So the flow duration curve representing the stream flow regime on a long term. For this site, a long term means 15 years of data. Okay? So far so good. You have the diagram, everything is in good order. Okay, this was figure 1, if you can follow the script. The following figures plot some different flow duration curves. Let me go back to figure 2. You probably can see a larger portion of the script. I can't, otherwise the resolution would not be suitable for you to read my fonts. So, as you can read in the script, the figure number 2 plots the empirical median annual flow duration curves, and in the background of the figure, all the empirical annual flow duration curves. So basically, for each and every year, it means 15 years of observation, the annual curve, and then on top of all of them, the median one. So a representation of the typical stream flow regime for a year that is typical from a climatic viewpoint. Okay? Okay. How does it work? If you can see the script, we open a plot, plotting just one annual flow duration curve. You don't have your script. Do you have the script in PDF? If you downloaded the PDF or the script itself, maybe you can follow, because you cannot see the entire line on my screen, unfortunately. So either you look at the screen of your colleague. Ah, Reza. Okay, that works. So we open a plot plotting a single annual flow duration curve. How? We use the vector of duration that we computed. You remember all the durations, and then look, QDM square parenthesis 1 comma nothing. We take the first row of the matrix where we stored for each and every row the observation, the sorted observation in a given year. So basically, if we send to the console these lines, it will open up a new plot where the annual flow duration curve will be plotted. If you see color RGB, you know what this instruction means? Exactly, it's another way to assign colors. We use the English word in other diagrams, like here, right? Black, or here, light gray. But R has several ways of assigning colors. This uses in relative term the red, green, and blue bands. So the following three numbers are in relative terms, the saturation in terms of red, of green, and blue. If the saturation, 30%, is the same for all the bands, the outcome is a gray shade. Okay, you can control gray shades like this, from white to black. Okay. The rest of the commands you know. I will send this to the console. Let me squeeze a bit, as usual, the panel with the script. I'm sending these lines only. See, what I see in the diagram now is a flow duration curve for a given year. Okay? Then, line 80. You see there's a for loop. The for loop does the following things. Lines is a way to add lines to an existing plot, the current plot, the one we just opened. We will use this plot with this axis and this setting to add additional series. Okay? How? With the for loop. If you look at the for loop, it goes from 2, because the first row we already used, it goes from 2 all the way down to the number of years of observation in the record. And for each and every for iteration, it will use the command lines. The command lines works very similar to the command plot, but it doesn't open a new plot, it adds lines. Okay? Sufficiently clear? Okay. And then it's exactly the same as the plot command, if you see. The X values and the Y values. And the Y values change at each and every iteration, because at each and every iteration I will select a different line of this matrix. The first one we use, we will start from the second all the way down to the 15th. Okay? Very good. So I'm simply, now let's get back to the standard size. I'm launching only the for loop. These are the 15 annual flow duration curve. If I want now to construct the median one, duration-wise, I'm going up and I identify the stream flow value that for that very duration exceeds 50% of the observation and is exceeded by 50%. As simple as that. We did this already. We stored actually the result of this operation in, if you recall, QPRC matrix. This object here, QPRC, let's have a look at it so that we remember. Here we already stored the median annual flow duration curve, the one for a very dry year and the one for a very wet year. 1 in 10 year, driest or wettest year. Okay? So what we're doing here will be to plot the second row. Why the second row? Because we want to plot the median annual flow duration curve. And we will add it on top with the black color and a width of the line 3 times in relative term the standard thickness. So it will be a very thick line. I'm launching this line. Tell me if you can follow me. And now if I zoom in, I see the flow duration curve for a typical year. I have to add a few final touches like axis, grid, and legend. Let me increase the plot for adding these elements so that the plot becomes more or less similar to yours. Okay, so far so good. Then the other figures are very, very similar. Let's read. Figure 3, empirical percentile annual flow duration curve, and in the background, the empirical. So gray lines in the background, and this time the one indicating a regime for a dry year, the one indicating a regime for a wet year. This would be figure number 3. I'm sending all the lines now because we understood how it works, correct? I didn't remember to squeeze the diagram, so the legend appeared in a not very nice way. Let's do it again, Sam. Okay, better. In your case, it should be even better. Okay, this is the representation. Wet year, 1 in 10 years on average. Dry year, 1 in 10 years on average. Okay, and in the background, all the annual curves. And then the last figure, if I'm not wrong, 4, yes. Then we move to task number 2, but we will address task number 2 next week. The last figure, there it is. It's a comparison, okay? It's a comparison for that side of all these empirical flow duration curves that we put together. You see the period of record flow duration curve. Now it's in green, okay? Median is still black, red and blue for the 2 percentile, as before. What I want to point out is that the indication of a typical, from a climatic viewpoint, regime, you can retrieve from either the period of record and the median annual flow duration curve for a duration range which is intermediate. You see, the 2 of them are very similar, up to the tails. Now, the tails, for a period of record flow duration curves, are controlled by anomalous years, okay? So the period of record goes down quite dramatically because of the presence in the data set of very dry years. This drop is not something you get every year. For regular years, this catchment has a perennial behavior. But on the long run, 15 years consequently, you may see a big drop which depends only on a few very dry years in the sample. Sufficiently clear? Okay? Good. So if you want to depict and represent what's going on an average or typical year, you look at the black line. If you want to see the real stream flow regime on the long term, 10 years or more, then you should refer to the period of record 1. Good. Do you have questions on this part? Okay, so we put now the practical activity on hold because we need to address more theoretical, let's say, elements to continue. So let me close this. When you close RStudio, I don't remember if I ever told you, when you close RStudio, it doesn't really matter to save the workspace, because if you noticed this morning, we simply ran all the lines and we were exactly in the same conditions where we were when we stopped. So doesn't really make sense to save the workspace. I'm closing it. I'm stopping the Teams call and I close this. Now, okay, let's go back to the slides. We saw the definition, we saw how to construct these curves. Now I want to show you how these curves can be used to address water resources management. I'll provide you only with a few examples. In the slides PDF version on Virtuale, if you are interested, there are more examples. In the paper, which I provided you with, a classical paper, you can find in Virtuale, in the zip archive with many papers, Vogel and Fennessy, 1995, you will find a series of examples of practical application of flow duration curve. If you read this list, which is not even conclusive, you will see that flow duration curves may be used with addressing several water-related problems: sedimentation, analysis of wetland behavior, hydropower potential studies, many waste load allocation, quality control. And the beauty of it is that through these curves, we can approach this problem in a diagrammatic way, meaning through images, through figures, diagrams that can be understood easily from water managers that do not have necessarily a background in statistics and in hydrology and in hydraulics, okay? Because you talk to them in graphical terms. So, clear enough? Did you understand what I'm saying? Okay, let's come to very classical uses of flow duration curves. Now, flow duration curves worldwide are used for characterizing stream flow regime in natural streams and rivers, okay? In various nations, there are various classification, let's say, criteria, but based on stream flow, we can depict, represent what flood flows are, high flows, intermediate, and low flows as the duration moves towards higher values. For example, typical low flow indices, Q95. It's used across, for example, North America. It's a way to characterize the low flow regime of a given stream. What is the meaning? It is just the discharge associated with the duration of 95%. Okay? It's a low flow index. In Italy, we don't use Q95. We use instead as a low flow index Q355. Why? Because in Italy, traditionally, we express duration not in relative terms, but in number of days in a year, okay? This is why. If you divide 355 by 365, you get, surprise, surprise, 97% duration. So very similar to what they do in UK, for example, and US. I don't know about your countries. I don't know if you know. Very common low flow indices to, let's say, characterize the flow regime when the amount of water is low. We have also high flow indices in Italy, Q10, so 10 days in a year, which is 3%. This is what we call in Italy the characteristic flood. A characteristic flood in a river is associated with a 10-day duration, and so on and so forth. This is one of the most general uses of flow duration curve. Flow duration curves can also be used to have a clear representation of hydrologic change. Okay? Because the climate is changing, because the land cover is changing, the hydrologic behavior of a river may change in time, right? So what you see here, it's a diagram with two different flow duration curves for the very same river and very same river cross-section. And 2 different years. We saw that the annual flow duration curve for a given river varies a lot because the climate is variable. 1 year rains more, 1 year rains less, so we expect to see variability. We plotted variabilities. We saw how to summarize it graphically, right? So you may say, these 2 years are simply different. The catchment is the same, the basin is the same, but years are different because 1 year was wetter than the other, right? And so you have a perennial stream that for a very dry year becomes an intermittent stream. Look, this flow duration curve here tells us that in the river there's discharge for less than 50% of the time in the year, so less than 6 months. The rest, discharge is zero, okay? But, I don't know if you can read the legend, these 2 years had a very similar rainfall amount, 879 millimeter, 887 millimeter. Given all the uncertainties, basically it rained the same amount of water in the same catchment these 2 years. Then what happened there? These 2 years are 8 years apart. The first year, black thick line, a pine plantation in this small catchment was planted. So pine trees were planted on the slopes, and they were still small. And this is the situation 8 years after. Pine trees have grown, their root system went down deep into the soil, okay? Interacting more effectively with groundwater, enhancing, increasing the evapotranspiration fluxes. As a result, during summertime, low flow season, the water that normally fed the river from groundwater flow when the slopes were pastures and field is not available any longer because the pine trees are using them. So, based on this plantation project, the regime changed dramatically and the stream became ephemeral in that river cross-section. Sufficiently clear? So it's not climate change, it's simply a land cover change, moving from fields, pastures, greenland to forests. This might be the impact, okay?
Which one can cause flood risk? These 2 graphs.
Very good. If you're concerned about flood risk, having forests is good. Normally, they slow down the catchment response. Normally they increase the infiltration, so having trees instead of pasture, definitely better for flood control problems. But if instead you are interested in using the water, available water, for irrigation during summertime or hydropower production, changing radically from pasture to forest might reduce a lot, might have an impact on your hydropower potential or volume of water you can use for irrigation. Is this clear? So thanks a lot for raising this point. Other questions, points? Okay, so representation of change. Representation of change induced by the presence of humans, anthropogenic change. Okay? Here you have a comparison for the same catchment, same river cross-section of the natural stream flow regime, blue, and some altered stream flow regime, due, for example, to the construction of a reservoir for hydropower potential. You build a reservoir, you store water in order to have a more regular discharge flowing in the river across time. What do you get? You get a flow duration curve that is flatter. You remember the first classes? Artificial reservoir, flatter curve. What is this instead? This is the case in which given river, I'm looking at the river from above, is used for hydropower production using a run of the river system, meaning without a reservoir. So part of the river with the barrage aware, part of the river discharge is diverted, sent to a hydropower plant producing hydropower electricity, and then return to the river only downstream. Okay? So you have a segment of the river now that sees less water. This produces an impact as indicated in this diagram. So the whole flow duration curve is lowered. So they are an effective way to represent change in stream flow regime due to natural causes, climatic causes, or anthropogenic causes. Is this sufficiently clear? Classification of stream flows, representation of changes, and now let's go to the good part, let's say. An approach to water resource management problem, sedimentation, navigation, in-stream water quality assessment. How? As I was saying before when we started, flow duration curves can be used to address a water management problem graphically by means of diagrams when there are clear relationships between the stream flow and the water resource index you are interested in. Okay? So, let's suppose we start from the flow duration curve, and let's suppose that this is rating curve in general. Rating curve we tend to associate to the relationship between water level and discharge. This is a rating curve in general. This is a water resources index, can be a water quality index, the amount of the concentration of a given pollutant, and the stream flow. Okay? In this case, there's an increasing, monotonically increasing relationship between this index and stream flow. For the sake of simplicity, let's suppose that this water resource index is the water level. Okay? If it's the water level, this is the rating curve that we discussed during the first classes of this course, right? So, combining the two diagrams, you can start with the given value of the water resource index, read the corresponding stream flow value, and through the flow duration curve, associate a duration to this value of the water resource index. Duration meaning percentage of time, but also meaning exceedance probability. You can use the definition you want. Binding the two diagrams, you can come up with a summarizing diagram that reports the water resource index you are interested in on the vertical axis, not the stream flow anymore, because there's a one-to-one relationship between the two. Okay? Water resource index and associated duration. These water resource duration curve come with many examples from the paper I was pointing out before, which is uploaded on Virtual in case you are interested. I will limit my presentation to 2 examples. One is particularly relevant for this class. So the first example I want to make is the study of wetland inundation. Okay? Let's suppose you have a one-to-one relationship between the river stage, so the water level in a given river cross-section, let's say here, okay? You have a one-to-one relationship between the river stage and the stream flow. This is what we called 3 weeks ago a rating curve in the strict sense. Water level or water depth, stream flow, right? Stream flow increases, water level increases in the river cross-section. Make sense? Then you can, with a flow duration curve, associate the stream flow to a given duration. Joining these two diagrams can be summarized in a single diagram that tells you the water level as a function of the duration. Let's suppose that in this area you have an orchard with fruit trees that are particularly sensitive to the presence of water, and they can stand water only if it stays there for, let's say, 2 weeks in a row, 20 days in a year, okay? Combining the information on the river stage with a digital elevation model, you get the amount of land that is inundated, wet, has the presence of water in time. You can represent, let's say, the duration of the flooding in time, which might be very informative for agriculture. Okay? This is not an approach for extreme flooding scenarios. You use a totally different approach, and who of you attended flood and drought risk management class? Those are the methods for extreme floods, meaning that you are concerned about the safety of people living in urban areas, for example. Catastrophic flood. This is not the way. This is a way to study the, let's say, dynamics of a wetland area, amount of flooded area in time. Let's suppose that you want to, let's say, exploit this area for agricultural purposes, and the presence of water doesn't go well with the presence of the vegetable you want to grow, or the presence of fruit trees. You understand? This is the water problem at hand. You can say, okay, that area would be good, but it gets flooded too often. So it's not good for a peach orchard, because peach trees will suffer a lot. Let's build a levee to reduce the frequency of the flooding of that area and protect that area from frequent flooding. You understand the point? What could be the advantage? The advantage you can summarize graphically. Here, the situation changed a bit. Rating curve was here, flow duration curve is here, right? Here instead you have stream flow exceedance probability. So this Panel C is the flow duration curve. Stream flow, river stage. Panel A is the rating curve. Now you have two additional panels, B and D. This is river stage damage. In the literature, this relationship, it's called damage model. Okay? You may find an example of damage model for agricultural problems or for urban environments. What does this panel say? That if the river stage increases, but the area where I have my orchard is not flooded because the water level is lower than the floodplain of the orchard, I get no damage. Then, as soon as the river stage exceeds a certain threshold, I start to have damages. And the damages increases with increasing values of the water level. The higher the water level, the larger the flooded area, the more the trees that were gonna die, okay? So these damage curve, as I said, you can find many examples. This one here is a set of curves developed for Europe, summarizing damages to, for example, residential buildings, this JRC model. Let's suppose we stick to agricultural problems. Let's say, the damaging, of course, there's a lot of uncertainty in damage model. These are simplification of reality, you understand this, okay? Empirical curves with a lot of noise behind them, but it is, let's say, sensible to say that if the water stage, river stage increases, the damage will increase, okay? Makes sense. So we can associate a given exceedance probability or duration to a stream flow, to a water level, to a damage value. And we can represent then the exceedance probability of the damage. Okay? Do you see that? Let's go like this. That perhaps helps for your colleague that will attend. So with a flow duration curve, I start with a relationship between duration or exceedance probability and stream flow. I turn it into a relationship with river stage, and finally into a relationship with damage. I can build this. This is the water resource index duration curve, a relationship between damage and exceedance probability. Now, the area below this curve, this is a geometrical representation of the expected damage. Okay? You follow me? Now, the agricultural owner, the manager, could say, okay, the damage, the expected damage is too high. Let's build a levee. A levee this tall. This will reduce the damages by far. Let's see how the situation changes. So, if I build a levee this tall, it means that the river stage can go as high as this point and the damage will be zero. Okay? I will start seeing damages only for river stages above this point. Do you follow me? And then, of course, above this point, there will be an increasing relationship again between river stage and damage, to simplify a very complex problem. Now, since the construction of this agricultural levee, the damage exceedance probability curve went down a lot. And now the expected damage is this area instead. So you can compare graphically different situations. Building a levee brings in some costs, okay? A damage is a loss, a cost, but also constructing a defense structure has some cost. With this graphical approach, you can compare the expected damage as the height of the levee goes up, and then the cost of the levee as the height of the levee goes up. You build a higher levee, you spend more money, right? So the stronger your defense system, the higher the cost and the less the loss. And what you are interested in is your total cost. So through a graphical comparison, you can identify the optimal solution, the optimal levee height that minimizes the overall cost, consisting of the cost for the mitigation measure and the cost you incurred in because your orchard gets flooded, okay? And this approach is very easy to understand, even from people who do not know anything about exceedance probability or stream flow values or discharges, no? Because you address the problem in graphical terms. Are there questions about this? Comments? Is this sufficiently clear? If you are interested in that paper, you can find example on water quality management, water allocation, and others addressed in a graphical way. I'll provide you with a final example which deals more closely with hydropower feasibility studies and how to produce water resources duration curves for assessing hydropower feasibility. Of course, we are referring in this case to run-of-the-river hydropower plant, meaning that there's no reservoir that controls the discharge we send to the turbine. We get the water as it comes in the natural stream, okay? Just diverting part of the discharge. Run-of-the-river power plant or reservoir power plants, two very different systems. The first one, you can hydropower feasibility studies, you can address with flow duration curve. You'll see this in simplified terms with me, and in the next module, you will analyze this in more detail and from a more technological viewpoint with my colleague Cristiana Bragalli. Okay? Good. So, do you know this relationship already? Have you ever seen this in your life? Yes? This is the power, and what we will build is something like this, a power duration curve. So, associating the hydroelectric power with a duration, and therefore with an exceedance probability. Now, that expression, power, is equal to, what is gamma?
9,400.
But what is it? What is it? In
Specific,
the specific weight of the water, right? So, from a dimensional point of view, gamma is what? Let's say a force, a weight, divided by specific weight. Force divided by what?
Square meter.
Square
meter.
No, dimensionally, but not square. It would be a surface. It's a weight per unit of volume. So minus 3 dimensionally. This is the specific weight times Q. Q is the discharge that was sent to the turbine. And this is what? What is the discharge? Dimensionally.
Volume over time.
So, volume over time. Very good. times what? H. What is H? The total overall hydraulic head. It's the water level difference between the intake of the turbine, where the inflow starts, and the tail water. This is, let's say, an amount of energy per unit weight of the water. It's a graphical representation of a quantity of energy, but dimensionally speaking, this is a depth, a height, okay? So, if we look dimensionally at this term, we see a force per unit volume multiplied a volume, so this and this simplifies themselves, per unit time per length. So, we see a force times a length, which is energy, per unit time. So dimensionally, this is a power. Okay? And if we want to see an example of the amount of power, now this, you told me already. Gamma is equal to what? Now, not dimensionally. What is its value? You know what gamma is? Gamma is gravity acceleration times rho. What is rho?
1,000.
No, it's 1,000 approximately.
Is the density of the water. Okay, so mass per unit volume times an acceleration gives you a force per unit volume. What is the value of G?
9806.
What? If you talk like this, I have no issues for her. If you talk like at least I have to be able to read your mouth.
9.81.
This is 9.81 watt. What?
kg per meter. Kg per meter.
Kg.
Or kilometer.
Ah, okay. Kilograms, mass kilograms,
Per meter. Cubic.
the acceleration. You're talking about the acceleration. It's an acceleration, right?
Yeah.
Gravity acceleration, kilogram. Can it work? No. So what is it, guys? Meters divided by square second, acceleration. Okay. What is rho? Density. Density is 1,000 watt. Now we have kilograms per cubic meters. Okay? And this is more or less equal to what? Almost 10,000, to simplify our job. Newton, which is the force units in the international system, divided by cubic meters. Okay? Force divided volume. More or less 10,000. Then let's suppose we have a discharge of 1 watt. Normally we measure discharges in
Cubic meter per second.
cubic meter per second, and an hydraulic head of 1 watt. International system, meter. Okay, so the power is what? 10,000 Newton divided by cubic meters times cubic meters per second. So Newton divided by second. Per meter. So Newton per meter joule divided by second watts. Okay? Which reads also 10 kilowatts. A discharge of 1 cubic meters per second and a difference, water level difference of 1 meter gives you already 10,000 watts, or I never know how to pronounce this in English. Sorry about that. Or kilowatt. What is the pronunciation? Kilowatt, like in Italian. Okay. Okay. So this is the power. And normally, for run-of-the-river, and we will see why, for run-of-the-river power plant, the power-discharge relationship is not monotonically increasing, monotonically decreasing, but it's very often a bell shape, okay? By increasing the discharge, you have a first part in which you increase also the power, the discharge sent to the turbine, but then beyond a certain discharge value, the power goes down. We will see why. Okay? Keep in mind that this is the expression for evaluating the power. So, as I said, bell-shaped power discharge rating curve plus flow duration curve returns something like this. This is a power duration curve. So here you have time. Here you have power. What is the meaning of this geometrical figure here? This area, what is the meaning? If you have power on the vertical axis and duration on the horizontal axis, which is another measure of time, percentage of time. What is the meaning of the integral of this curve? Energy. So you have a graphical representation of the energy you can produce, and then it depends. What is the flow duration curve you're using? The period of record one. So that's the energy with that turbine you can produce in the long run. Or flow duration curve is the median annual flow duration curve. So this is a typical year. The area below the curve will be the energy in a typical year with that turbine. You change the turbine, the curve changes, less energy. So you have a graphical representation of the energy in the diagram. It's just the area below this curve. This already combines a turbine with a hydraulic head, so the who designed the plant is making choices. Should I select turbine A, turbine B? Comparing areas can tell you directly the hydropower potential of that plant. Okay? This on a qualitative level. An example that perhaps, let's say, explains why the power stream flow relationship is a bell-shaped curve. Okay? Real world example. We are in Italy. This is the Po River. Okay? This is upstream. This is downstream. The Po River is this river here in northern Italy, is our largest and longest river. There is a run of the river power plant on the Po River. So let's say a hydropower plant that uses the water flowing in the Po without the, let's say, the construction of a proper reservoir. There's no reservoir. There's a large dam, and then, look, a meander, a long one. These are kilometers of the river Po. large meander, and then with an artificial channel, this meander was cut. Okay? Since the meander was cut, the elevation here and elevation here stays the same, right? But shortening a lot the distance by connecting directly these 2 points with an artificial channels provides you with some head to exploit in order to produce electricity. Okay? The electricity is produced by the power plant, which is this one here. This is the diversion channel. It's an artificial channel. Here you have the dam. The dam is a big dam consisting in more than 10, I think 12 if I recall it correctly, 12 gates that can be controlled. Okay, these are control gates that can be open or closed. And through these gates that can be open or closed, operators, manager, can control the water level upstream. Okay? So if the discharge is low, they basically close these gates so that the water level upstream stays high. If the water increases instead, they open partially the gates so that the water level doesn't increase further. The goal is to maintain the water level here upstream the power plant more or less constant regardless of the stream flow coming from upstream. Okay? They want to manage the water level and keep it constant. So when the discharge is high, the water level is high on its own, but when the discharge is low, the water level will go down. Controlling the gates in the dam, they keep the water level high. The water level high is what governs the hydraulic head between the intake and the tail water. Okay? Because the tail water instead is controlled by the water level downstream. Okay, the water level downstream propagates and controls the water level at the tail water, whereas the water level at the intake is controlled by the gates. So they can control the hydraulic head depending on the current stream flow regime. Sufficiently clear? Here you have some specs of this hydropower plant. It's, of course, the largest run-of-the-river hydropower plant in Italy. Depending on the stream flow regime, the effective hydraulic head varies between 3.5 and 11 meters. Okay, we'll see additional details on this. The maximum usable discharge is set. And it's set by the set of the array of turbines that are installed. You cannot use more than 1,000 cubic meters per second, which is already a lot. Okay? There are 4 turbines, huge, big, almost 8 meters of diameter. So the propeller is 8 meters wide. And the maximum power is 80 megawatts. The average flow through the turbines it's 800 cubic meters per second. Okay? So very easily, if you use that formula, 800 cubic meters per second and if you are lucky, 10 meters of effective hydraulic head returns 80 megawatts. Okay? Very good. This is instead a hydrologic feature. The River Po historically had a maximum discharge in this point of almost 13,000 cubic meters per second. Of course, when there's a huge flood with return period of 50 years or above, the power plant is closed because there are all sorts of sediments traveling with the discharge, so they do not produce energy during major flood, very major flood. They can use minor floods to produce energy. So far, so good? We'll skip the break today as well. Is that okay for you? And we'll finish earlier, maybe. Maybe. So, from above, again, River Po, this is the dam, these are the 4 turbines, the intake, the tailwater, and the ship lock. You know what a ship lock is? The River Po is used also as a mean of communication for example, little commercial boats or fisherman boats. So you have to be able to cross this river cross section to navigate upstream, but you cannot because there's a dam. So what you do is to build a ship lock. A ship lock is a system in which you can connect by closing gates, closing and opening gates, two points with a different water level. They have several in the Netherlands. You've never seen a ship lock in your life? Panama Channel, for example. Ship lock. So this is an example. This is the tailwater. Pronto intervento. How do we close this? This is the tailwater and this is the intake. The water level is different. The boat can arrive. This gate is open. The boat goes in. The gate is closed and through an hydraulic system, the chamber is filled of water. Then this gate is open and the boat can flow, can navigate upstream. Okay? Through a system like this, the Panama Channel works, for example. You've never seen ship locks before? You did see. Okay. Okay. Dam, intake, the powerhouse, the tailwater, and the ship lock, as we were saying. This is instead a section of the powerhouse. The section is here, and we're looking at the powerhouse from here. Intake, this is the pipe that connects to the Kaplan turbines. Kaplan turbines have normally vertical axis. And the amount of water, the turbine water flowing in makes the turbine spin and the generator spin that produces electric energy. Then the water gets here, tailwater. The elevation difference between tailwater and intake is the effective hydraulic head, that is, you converted into electric energy. Now, what happens? Let's suppose this is the flow duration curve for the natural stream flow of the Po River in that river cross section. Okay? Can we use all this water? No, we cannot. As we said before, there's a maximum discharge that can be used by the turbine, 1,000 cubic meters per second, right? Plus, we will see this during next classes, there are normally regulation that prevent you to use all the water that is flowing in a river to protect natural habitats in river as well. But let's suppose that this is the amount of water that is flowing in the river. We know that the maximum discharge we can turbine is capped to 1,000 cubic meters per second. Our turbine set array cannot use higher discharges, okay? So basically this is the flow duration curve of the usable discharge, okay? On the same diagram, let's plot, of course on a different axis, the upstream water level and the downstream water level associated with a given duration, so a given discharge value. What do you see here? The upstream water level is constant. How come this is constant? Speak up, please. How come this is constant? No matter what the discharge is, the duration is, the water level upstream is constant. Why? We saw it 5 minutes ago. How come it's constant? It doesn't change. The upstream water level. So the water level here, no matter what the stream flow is constant. Why?
It isn't disturbed. It isn't disturbed.
In a river, if the discharge increases, the water level should increase, right? And instead, in this diagram, for a very high stream flow value, I have an upstream water level that is here. And for a very low stream flow value, I still have a water level that is here. Why? I told you this a few minutes ago. Because there's the control dam. Operating the gates, I manage to keep more or less the upstream water level constant. Okay? I manage it to be this way. Opening and closing the gates. When there are high discharge value flowing in the river, gates are open and the water level is at its maximum. If the discharge goes down, I start closing the gates in order to keep the upstream water level constant. Okay? Is it clear now? Or you have doubts? You follow me? I lost you. We should have taken the break. I lost you.
If you open the control switch, it doesn't decrease the upstream water level?
This is a reference value of the upstream water level, okay? A reference value. Let's say it's the water level that the managers of the power plant want to have in the upstream point, in the intake. They manage to keep throughout the year the water level constant by opening and closing the gates. Okay? So, if the dam wasn't there and the gates weren't there, if a higher discharge would mean a higher water level. Okay? But now the dam is there, and a lower discharge would mean a lower water level. But now the dam is there. And with the gates, you can control the water level. And you do so in such a way that you try to keep the water level constant throughout the year. So this is why, no matter what the natural stream flow is, the upstream water level stays constant. This doesn't happen in the tailwater. Why? Because there, the situation, the conditions are controlled by the natural stream. Okay? So, if the discharge is low, you will have a low water level in the tailwater. If the discharge is higher, you will have a higher water level in the tailwater. If the discharge is super high, you will have a super high water level in the tailwater. Why? I say this again, because the water level here is controlled by the stream flow that is flowing through the main channel, okay? When the stream flow is low, the water level, stream flow actually is divided in two. When the stream flow is low, water level here is not controlled by a dam, like in this case. So when the stream flow is low, water level is low. When the stream flow is high, water level is high. You are interested in the hydraulic head. What is, by definition, the hydraulic head? The height difference between upstream and downstream. So the hydraulic head, this term, is not constant. When you have the highest discharge, the head is the lowest. When you have the lowest discharge, the head is the highest. Okay? And power is gamma, which is constant, multiplied by Q, multiplied by the head. So when the discharge is high, the head is low. When the discharge is low, the head is high. This is why the power duration curve is normally a bell, because it is the multiplication between the available head and the usable discharge. Okay? One goes down while the other one goes up. So multiplying the two will result in a bell-shaped power duration curve. This is normal for run-of-the-river power plants. Okay? Very normal. And the area below the curve is energy, even dimensionally. Good? Good. Okay. Let's start to address, but we will stop in 15 minutes or so I keep my word. Let's start to address a new topic. So far, I hope I was successful in underlining how important this graphical representation of the stream flow regime is and how we can easily construct it starting from observed data. So observed discharge values, okay? But in the majority of cases, the river cross-section we are interested in will have zero observation, no data at all. Still, we want to check if the possible hydropower plant is economically feasible or not. So we want to predict the stream flow duration curve without data. Then, of course, it takes years to design, develop, build a power plant. Meanwhile, I will start taking measures, right? But in order to have an idea, it's standard practice in hydrology to make predictions without data. This can be done through hydrological simulation that use hydrological models, or can be done through regionalization techniques. We will consider these as these are the most common tools that are used to make a prediction in engaged catchments. Regionalization. What does it mean? It means considering observation collected in different catchments, but with similarity in terms of climate and hydrologic regime, and use these observations, transferring them into your target site, which is engaged. Okay? These are statistical regionalization procedure. So, to summarize, the duration curves and other representation of the regime are very important. They can be constructed if we have data, and the construction is straightforward. We sort the observation in ascending or descending order, and we assign a duration to each and every observation in the sorted sample. Very easy, But the reality is that very often we do not have data. We do not have even spot measuring campaigns. So we need to predict these, let's say, design variables without any observation of discharge. We will see an easy approach that shows to you, exemplifies to you how this can be addressed if we do have data in different catchments. We don't have data where we want them, but we have data elsewhere, and this is a common situation. So we will see how a flow duration curve can be predicted using data collected in a region. We will see how to set up particular models that predict stream flow indices based on catchment characteristic. And then we will see how this catchment characteristic can be, let's say, derived in a GIS environment. So, prediction in engaged catchment through regionalization. Let's suppose you would like to assess the hydropower potential here for a runoff of the river plant. You don't have any discharge data here, but you do have data in all these catchments that show similarities from a climatic viewpoint and from a morphological viewpoint, so same, let's say, morphological features, same geological units, so you expect these catchments to behave similarly. We will see a very easy way to transfer hydrologic information from these dots, these gauging station, to the ungauged river cross-section to make some prediction, okay? The model I will refer to is one of the simplest presented in the literature, but also one of the most robust in making the prediction. It takes advantages of the fact that where we do have stream flow observation, we have a lot of them. Because if we have just a couple of years of data, we have more than 700 observation of daily stream flow, okay? If the years are 10 in a given river cross-section, I have thousands of observation, okay, of daily stream flow. So it is also referred in the literature as a graphical regional model. It's mostly non-parametric. It doesn't use mathematical formulation to represent the duration. It's solely based on observation. Its main idea is very simple. The flow duration curve is what? Flow duration curve, as we know, is a representation of stream flow with duration, right? Here I have stream flow, and here I have duration, and this is the discharge or stream flow associated, sorry, this is duration D, sorry about that, and this is the discharge associated with the duration D star, okay? So this approach says that the discharge associated with a given duration, I should take breaks myself, I become tired if I don't. Help me remember to take breaks, okay, during classes. Discharge associated with a given duration can be seen as the product of two terms. An index flow in cubic meters per second, and then a dimensionless index associated with the duration. As you can read here, it can be expressed as the mean annual flow, so the average stream flow on the long run, the average value of daily stream flow across several years, an average value that is characteristic for a given catchment, and it's a discharge in the strict sense, cubic meters per second, times a dimensionless discharge, lowercase q, that expresses the relationship between the mean annual flow and the duration, and this instead has a regional validity. So the method assumes that is the same, that lowercase q duration is the same for all catchments that are hydrologically similar. Okay, that have the same climate, that have the same geology, same slope, same morphological feature. This has a regional validity. This instead is site specific. It's really for Savio et San Carlo, whereas this is the same for all the catchments that are similar from a hydrological viewpoint to Savio et San Carlo. Okay? So basically what you do when you apply this model is to standardize the flow duration curve, divide the discharge by the mean annual flow to get a dimensionless discharge, which you estimate based on regional information. This becomes fused, V star divided by M and F, and this is the same. MAF. Did you understand what MAF is? I'll try to be even clearer about MAF. It's very important. It's our index flow. Let's say the identity card, the signature of a given site, because this term instead is regional, as a regional value. How do you retrieve MAF? If you have data. This is time, not duration, time. This is discharge, and this is a series, long series of daily discharge, maybe several years, okay? Several years of daily stream flows. MAF is nothing else than the mean value. Okay, this is MAF, mean annual flow, it's said in the literature. But what it is really, it's the average daily stream flow computed over a long term. Okay? This term is site-specific. This has a regional validity. So, what do? To get it for an engaged site, you use the lowercase q relationship that you obtain by averaging several empirical dimensionless flow duration curves you construct from data observed at catchments that are similar to your site of interest. Okay, I'll show you some example, and then this will become the core activity of the last part of our practical application. This is a portion of central Apennine in Italy. This is the Apennine divide, and all the dots there where you see numbers are conventional site ID used by the agency that provided us with data, and all these observed data belong to catchments. And using a graphical procedure in this study, the study area was divided by sub-region with very similar hydrologic behavior. Okay? So up here you have catchments that have very low permeability compared to catchment down here that from a climatic viewpoint are not that different. The area is a small portion of Italy, more or less. So from a climatic viewpoint, these are all catchments looking at the Adriatic Sea. the main precipitation system come from east or northeast. They share more or less the same climate. So the problem is not really the climate there, the problem is geology. And geology changes a lot from north to south of this district. Here you have hills like the one we have in Bologna with clay rocks, very low permeability. Down here instead you have limestone, fractured limestone with karst phenomena. You know what karst phenomena is? So really fractures that are opened by acidic rainfall events. So you have tunnels. So very high permeability and even some part of the water that flows in natural channels underground instead of that on the surface. So very different permeability from now north to south. And then another situation, these dark green catchments, these are low elevation catchments because the Apennine divide is up here. Here you have Gran Sasso, so elevations here are very high, 2,500 meters above the sea level. Instead, these smaller catchments here are all coastal catchment with fine sediments, so rather impervious as well. These are the different situations you may encounter in the study area, just to show you how the geology can control, like climate, and even more so sometimes, geology can control the hydrologic regime. And these are the two components of the regional model. I told you that the regional model is the multiplication of mean annual flow and a dimensionless flow duration curve. Here you see the dimensionless flow duration curves that were obtained as the average. For example, the yellow curve is the average of all the dimensionless flow duration curve that you can construct for this group of catchments. The brown one is the average of the empirical dimensionless flow duration curves of all these catchments in this region. Okay? So, your target site without observation is here. You pick the brown curve. Your catchment without observation belongs to this large system of karst catchment. You pick the blue curve. Your catchment belongs to the coastal, smaller and low elevation catchment. So it's a river cross-section here with a catchment that is coastal and low elevation. You pick the green curve. Okay? Let's see some common feature we already discussed together during the course. What did I say? Northern portion is impervious, much more impervious than southern portion. Look at the flow duration curve. Steeper here, and definitely purple, blue, much flatter here. Okay? Then I said to you, the coastal small catchments are all with fine sediment. They are basically, they consist of floodplains mostly, with low permeability. Again, very steep curve. This axis is dimensionless, as we were saying. So 1, not 1 cubic meters per second, 1 time the mean annual flow. 10, 1, 0.1. Question for you. They all start here. We're used to see flow duration curve like this. We said that the mean annual flow is the mean value, so I expect the mean annual flow to be somewhere around here. So the curves should cross. Instead, they seem to be starting all at the same point. Why? The answer is on the diagram. Can you see why on the diagram? Look at the diagram carefully. Look in particular at the horizontal axis. What do you notice on the horizontal axis?
It starts at 0.3.
It's a partial portion of the flow duration curve. It starts from 0.3. When we perform this study in which we compare all the methods available at that time to predict with regionalization procedure flow duration curve, and then we suggested, indicated the graphical one because it was simple and robust and provided prediction with uncertainty that was comparable to much more complex model. When we performed the study, we were working for doing scientific research in collaboration with Enel, which is our national electric board. Now it's a private company. In the past, it used to be a public body. Now it's privately owned. It manages the majority of hydropower plants across Italy. They are not interested in low duration. Why? Because low duration, it's the portion where you have high flows. When you have high flows, you do not produce electric energy because of sediment transport, what we were discussing. So the electric power plant manager are interested on the right portion of the flow duration curve, intermediate flows and low flow. This is the portion that is the most interesting to them. Also because when the flows are high, you can produce hydropower, right? You have water. Whereas you are concerned when the flows are low, if you want to quantify the hydropower potential, right? So high duration. So they expressly indicated interest on this portion of the flow duration curve, from 0.3 to 1. And what do we see from this portion? That more or less, wherever the region is, the mean annual flow normally is associated with a duration of 30%. Okay? Because the fact that they all intersect each other here, and here you see 1, it means that this is the duration associated with the mean annual flow. Okay? Sufficiently clear? So, you have a catchment here in the yellow zone. I pick this curve and this is the flow duration curve. No, because this is dimensionless. Okay? I still have to predict for that catchment the index flow, the mean annual flow. And if I don't have data, I cannot take simply the average because I don't have data. So this problem is normally in hydrology addressed with multiple regression model. So during the study, we set up multiple regression models that predicted mean annual flow as a function of several catchment descriptors. Area, elevation difference between average elevation and elevation of the outlet, the length of the main channel, and the mean annual net precipitation, millimeters, kilometers, meters, square kilometers, cubic meters per second. This is an empirical model that performs well for this region. Do not dare to take that mathematical expression and apply it at your home district, because it won't work. This is a statistical model that works in this area. These ugly numbers are statistical coefficients that need to be identified for your study region. And we will see how we can do this. What is the important thing to note? The important thing to notice is that none of these variables depends on discharge. So this model provides you with an estimate of the mean annual flow without any information of the discharge. You not just need to know the size of your catchment. Of course, we expect the size to be important, how big it is. Then elevation, mean elevation relative to the outlet, and main channel slope is main channel length is an indication of slope. So how steep is your catchment, how much rain your catchment gets, and based on this information that nowadays you can easily retrieve in a GIS environment, you can produce a prediction of the mean annual flow. Then it's done. You have the mean annual flow predicted on the basis of catchment descriptors. You remember the table I included in the practical activity description? There was a table of catchment descriptors. You predict this with catchment descriptors. You get this from the average regional curve, and you have a prediction of your flow duration curves. The last part of our practical activity will be dedicated to the construction of a regional method like this. There are still a few details we have to see from a theoretical viewpoint, but I believe that we'll be able to start working on the project on Monday. So on Monday, please do bring your laptop. Okay? Ciao. See you on Monday.